Sorry I had to cut you off there, but YouTube gets really mad when your videos are over 10 minutes. So we're going to do like a 5-minute other video. Okay, so this all should sound very familiar. It should sound like dialysis. When your kidneys aren't filtering stuff, we do it ourselves. Actually, dialysis is the pores in a dialysis membrane allow both solvent molecules and small solute particles to pass through. We don't really want that. We don't really want that. If your kidneys are not working, we're not super excited about that. So dialysis allows both solvent molecules and solute particles to pass through. Not ideal. Remember, not super what we want. What we want is hemodialysis. This is used to clean the blood of patients whose kidneys malfunction. So when the nephron of your kidney is not doing this, we make a little semi-permeable membrane from dialysis tubing, which we will play with in lab, and we perform this hemodialysis for you. So it is slightly different than dialysis. This blood is diverted from the body and pumped through a long cellophane dialysis tube suspended in an isotonic solution. Not in water, not in syrup, in an isotonic solution, just like your blood. And your blood is able to, small waste materials such as urea pass through the dialysis membrane and are washed away, just like what your kidneys do. This hemodialysis does the same thing. So this is exactly the difference between dialysis and hemodialysis. Protein molecules do not cross semi-permeable membranes and thus play an essential role in determining the osmolarity of body fluids. So your blood cells don't leave during dialysis, during kidneys, nothing. Your blood cells don't leave. The proteins in your blood stay right there because they're big old chunks of protein. They can't get out of the semi-permeable membrane. They're the gummy bears in the pantyhose. They can't get out. The grid is like this and they can't, like, let me out, and they can't get out. So this determines a lot of the osmolarity in your blood. If you have a high concentration of these proteins, then again, what's water going to do? It's going to rush in there. It's going to say, I've got to dilute it. I have to dilute it. It's like, think of water as this nervous little thing that's like, I've got to dilute it. And it's always going to rush in there and try and dilute it. So this is why when we get to physiology, protein is going to play a real serious role in the movement of these body fluids. The pressure of the blood inside the capillaries tends to push water out of the plasma. We're going to get to the picture of that, so just hold on. I know you want to know. You're like, I need to know. I need to know. The pressure of blood inside the capillary, right? Let's go to the next one, then we'll look at a picture. The osmotic pressure of colloidal protein molecules tend to draw water into the plasma. So let's look at a picture of this. Okay, so here's our fresh, awesome, oxygenated blood. This is like, woohoo! This is awesome blood right here. And it has all this good oxygen in it, and the oxygen's going to come down here. This is your big toe cell, and your big toe cell is like, dude, I need some oxygen. And it's going to go from a high concentration to a low concentration. And all kinds of other things that can flow out of here. Now, not your red blood cells, not your proteins, not the stuff that needs to stay in your blood. But if there's good nutrients or anything in here, that'll flow right into here until it gets to equilibrium. Now, there's also a low concentration of CO2 in here because it's the sweet good blood, right? It's like, sweet oxygenated blood straight from the lungs. Coming down here, here's some oxygen. Now what's going to happen? It's going to take the CO2. Oh, this is the crap blood right here. It's got all kinds of crap in it. And all this is going to happen through osmosis and diffusion. Your body doesn't have to do anything. It just does it by itself. It drops off the oxygen, the nutrients, the raw materials to your big toe. Here's your big toe cells, and the big toe cells like, hey, while you guys are there, can you take the CO2? Just take it, please. Take it and breathe it out. So the arterial end is where filtration is favored. This is where you're getting all this great filtration. The venous end, that's this end going back up, this is the crap blood. Reabsorption is favored. So all the good stuff flows out, and then you got this pressure gradient here. Now you're low on O2, so it's not going anywhere. You've equalized the concentration of O2, and you've equalized the nutrients and everything is equal. But here now you had a low concentration of CO2, and it's going to swoop it up and take it back. And so all the kind of yucky stuff is going to go back up. It's amazing. Your body just does all of this through osmosis and diffusion and gas law, and it's fascinating. Again, reabsorption is favored, and waste products from metabolism enter the bloodstream, and that's where it goes back up and gets cleaned. Okay, so there you go. That is just the quick end of chapter 9, so you have all of the notes. If you need anything, let me know, and I will see you tomorrow on Monday.